Cryptography, the art and science of securing information, has played a crucial role in human communication for centuries. From secret wartime messages to the everyday protection of digital data, cryptography has consistently adapted to meet evolving security demands. Two fascinating aspects of this field, primers and frequency analysis, highlight the balance between creating secure systems and unraveling them. What are primers in cryptography? Primers, often referred to as keys or initialization values, serve as the foundation for encryption algorithms. Think of a primer as the starting point or secret ingredient that shapes how plain text is converted into ciphertext, an unreadable format for anyone who doesn't have the key. Primers are central to both symmetric and asymmetric encryption methods. Symmetric encryption and the role of primers. In symmetric encryption, the same key, or primer, is used to encrypt and decrypt data. Algorithms like AES Advanced Encryption Standard rely on these primers to securely transform information. For example, if Alice wants to send an encrypted message to Bob, both must share the same key. Beforehand, this shared key acts as the primer for the encryption process. One of the challenges with symmetric encryption is key management. If the primer falls into the wrong hands, an adversary could easily decrypt the data. Therefore, secure methods for storing and exchanging keys are essential to maintaining confidentiality. Asymmetric encryption, a primer. Evolution. Asymmetric encryption introduces a pair of keys, a public key and a private key, eliminating the need for shared keys between parties. Primers in this context are still vital, as they determine the mathematical relationship between the key pair. For example, RSA Rivest-Shamir-Edelman encryption uses large prime numbers as the basis for generating keys, making brute force attacks virtually impossible with modern computing power. Frequency analysis, the codebreaker's tool. While primers focus on building security, frequency analysis is a technique used to break it, primarily targeting simpler ciphers like substitution and transposition. This approach relies on the statistical properties of natural language and patterns within encrypted text, the birth of frequency analysis. Frequency analysis has its roots in the work of Islamic scholar Al-Kindi, who introduced the technique in the 9th century. Al-Kindi's insights laid the groundwork for systematic code-breaking. By analyzing letter frequencies in ciphertext and comparing them to the known distribution of letters in a language, how frequency analysis works. To crack a cipher using frequency analysis, cryptanalysts study the frequency distribution of characters or symbols in the encrypted message. In English, for instance, the letter E appears more frequently than Q or Z. This predictable pattern helps codebreakers identify correspondences between ciphertext and plaintext. For example, consider a substitution cipher where E is replaced with X. Analyzing the ciphertext reveals that X occurs significantly more often than other letters, hinting at its substitution for E. Once this pattern is established, other letters can be deciphered to reconstruct the original message. Historical applications. Frequency analysis played a pivotal role in decoding encrypted messages during wars and espionage activities. One famous example is the effort to crack the Enigma machine during World War II. While the enigma's encryption was far more complex than simple substitution ciphers, techniques like frequency analysis were foundational in breaking the code, supplemented by innovations in computing and mathematical logic, modern cryptography, and frequency analysis. The advent of advanced encryption algorithms has significantly diminished the effectiveness of frequency analysis against secure systems. Techniques like AES and ECC elliptic curve cryptography incorporate randomness and mathematical complexity, rendering statistical patterns nearly invisible. However, frequency analysis remains relevant in fields beyond cryptography. For instance, it inspires approaches in natural language processing (NLP), where algorithms analyze text patterns for sentiment analysis or translation. Additionally, the principles of frequency analysis find applications in machine learning models designed to interpret language, securing primers, challenges, and innovations. As encryption methods evolve, so do the strategies for securing primers. From physical safeguards to quantum cryptography, ensuring the safety of primers is paramount in protecting sensitive information. Physical security measures. Traditionally, primers were stored in secure facilities or transmitted using physical methods. During World War II, keys were distributed in locked containers to ensure their confidentiality. While effective, these methods were labor-intensive and prone to logistical challenges. Digital key management systems. Today, digital key management systems have revolutionized the handling of primers. By automating storage, distribution, and rotation, these systems reduce human error and streamline operations. For example, organizations use hardware security modules (HSMIS) to securely generate and store cryptographic keys. Quantum key distribution. Quantum cryptography represents a breakthrough in securing primers. Using the principles of quantum mechanics, quantum key distribution (QKD) ensures that any attempt to intercept the key alters its state, immediately alerting the sender and receiver. This innovation promises unprecedented levels of security, particularly for sensitive government and financial data. Beyond cryptography, broader impacts. Primers and frequency analysis extend their influence to areas beyond secure communication. For example, primers are integral to blockchain technology, where they facilitate secure transactions, and digital signatures. Frequency analysis, on the other hand, contributes to data analysis techniques across industries, from marketing to healthcare. Blockchain and cryptographic primers. In blockchain systems, primers are used to secure transactions and authenticate participants. Public and private keys ensure that only authorized individuals can access or modify data, maintaining the integrity of decentralized networks. Frequency analysis in data science. Frequency analysis has evolved into a tool for analyzing large datasets, enabling organizations to uncover patterns and trends. For instance, marketers use frequency analysis to identify popular keywords in customer reviews, while healthcare providers apply it to detect anomalies in patient records. Conclusion: a dynamic balance. Cryptography thrives on the interplay between innovation and deconstruction. Primers serve as the cornerstone for building secure systems, while frequency analysis reflects the ingenuity of human problem-solving in decoding them. As technology continues to advance, the balance between these forces will shape the future of secure communication and inspire applications across diverse fields. Whether you're encrypting a child-friendly narrative about Benny the Bear or diving into the technicalities of cryptographic systems, understanding primers and frequency analysis opens doors to new possibilities. So, how will you harness the power of cryptography today?